Good day, I am Dr. Ohlhoff and I will be handling this discussion of Assignment 7. So let's immediately start with the first problem. The first step in solving this question is to make a drawing of the triangle and to name the sides of the triangle. We also need a relationship between the various sides of the triangle. Fortunately, we can use the theorem of Pythagoras to find this, and you should be able to see that z, the length of the hypotenuse, is equal to the positive root of the squares of the other two sides. So we now have an expression for z in terms of x and y, and what was given is that the x dt is 2 centimeters per second and the y dt is 1 centimeter per second. We can now proceed to find the z dt. The diagram on the far right of the screen shows the relationship. Z is a function of x and y, and x and y are each functions only of t, where t in this case represents time. So dz dt is dz dx, dx dt, plus dz dy, dy dt. Note that the derivatives of z with respect to x and y are partial derivatives. We then calculate these derivatives, remembering that the x dt is equal to 2 and the y dt is equal to 1. Finally, we must find the value of the z dt at the point when x is equal to 6 and y is equal to 8. The calculations show that the z dt is equal to 2. Therefore, the length of the hypotenuse changes at the rate of 2 centimeters per second. That concludes the discussion of the first problem. So let's have a look at problem number 2. You can see that was given is that u is a function of x and x and y in turn are both functions of s and t. This is summarized in the diagram on the right hand of the side of the screen. We can now evaluate the partial derivative of u with respect to s. The u ds is the u dx times the x ds plus the u dy times the y ds according to the chain rule. In the next step, we have to calculate all the derivatives. Note that we have not been given an explicit relationship for u in terms of x and y. Therefore, we cannot evaluate the expressions the u dx and the u dy, and therefore we leave them as they are. However, we do have explicit formulas for x and y in terms of s and t, so we can evaluate the x ds and the y ds, and you can see the answers that are shown there. We must now calculate the second order derivative of u with respect to s. To do this, there are a couple of things that we need to consider. The first thing that you need to realize is that the partial derivative du dx is again a function of x and y, and x and y still remain functions of s and t. This is shown by the second diagram on the right-hand side of the screen. The second point that you must keep in mind is that each of the two terms in the expression for the u ds are products of two functions of s. Let us now find the derivative of the first term of the u ds. In calculating the derivative with respect to s of the first term, which is underlined in red, we treat this as a product. Hence, we write down du dx and we find the derivative with respect to s of the other factor, which is e to the power s times cos t, plus then we write down the e to the power s times cos t, and we have to find the derivative of du dx with respect to s. Next, we have to find the derivative with respect to s of the second term in du ds. That is the term underlined in blue. Again, we treat this as a product of two functions, so we first write down du dy and then we multiply with the derivative with respect to s of the second factor, which is e to the power s times sin of t. Then we have to write down the second term, which was e to the power s times sin of t, multiplied by the derivative with respect to s of du dy. In the next step, we evaluate all the partial derivatives. The first one is quite easy. If we look at the derivative with respect to s of e to the s cos t, we know that the derivative of e to the s is just e to the s. So that gives us this term here. If we look at the second part, the derivative with respect to s of du dx, we have to apply the chain rule. So this part here gives us this according to the chain rule. Let's have a look at the partial derivatives in the second line. Again, if we look at this partial derivative, we know that the derivative of e to the s is just e to the s. So we get e to the s times sin of t. For the second part, if we look at this partial derivative, we have to apply the chain rule because the u dy is also a function of x and y. That gives us this expression over here. We must now evaluate the expression that we obtained by applying the chain rule. So let's have a look at the various terms. If we look at the partial derivative with respect to x of the u dx, we get the second order partial derivative of u with respect to x. If we have a look at the partial derivative of x with respect to s, that just gives us e to the s cos t, because the derivative of e to the s is just e to the s. Likewise, if we have a look at the second part there, the partial derivative with respect to y of the u dx gives us a second order mixed partial derivative, first with respect to x and then with respect to y. And again, the partial derivative of y with respect to s is just e to the s times sin of t, because the derivative of e to the s is just e to the s. Let's also have a look at the partial derivatives in the second line. If we start with the partial derivative of du dy with respect to dx, we get this mixed second order partial derivative, first with respect to y and then with respect to x. If we have a look at the partial derivative with respect to x, with respect to s of x, that just gives us e to the s cos t, because the derivative of e to the power s is just e to the power s. Again, if we have a look at this expression here, the partial derivative with respect to y of the u dy, that gives us the second order derivative of u with respect to y. And finally, the derivative of y with respect to s is just e to the power s sin of t. We now simplify the last result that we obtained by removing the brackets. So let's see where the different terms go. If we look at this product, then we get this term here, e to the power 2s times cos squared of t. If we look at this product here, then we get this term over here, e to the power 2s times sin of t cos of t. If we look at this product here, then we get this term over here, e to the power 2s times sin of t cos t. And finally, if we look at that product, we get e to the power 2s times sin squared of t. We have now developed an expression for the second derivative of u with respect to s that is given in the equation that we've labeled a. In a similar way, we can find an expression for the second derivative of u with respect to t. You can find the full details of that in the memo of this assignment. To obtain the final result, we now need to add the equations a and b. You will notice that many of the terms fall away. Let me give you an example. In equation a, we have that expression, and in equation b, we have this expression. Those two obviously cancel out. Also, if you look at this term containing the mixed second order partial derivative of u, then you can see for that term in equation a, there is a similar term in equation b, and again, those two terms cancel out. We end up with an equation that contains terms like cosine squared of t plus sine squared of t, which we know is equal to 1, and that gives us the required result. That concludes the discussion of problem 2. Now let's have a look at problem number 3. It is clear that the requirements of the implicit function theorem are met. We can see that it's given that the first order partial derivatives of f are continuous and non-zero, and it's given that the equation f at x, y, z equals 0 implicitly defines each of the three variables in terms of the other two. That means that we can find the partial derivatives of z, x, and y using the implicit function theorem, and this gives us the following results. As you can see that, for example, the partial derivative of z with respect to x is found exactly in the way that is formulated in the implicit function theorem. To obtain the required result, we now have to find the product of these three partial derivatives. As you can see, there are various common factors in this product. I will mark these for you. Since it is given that each of these partial derivatives are not zero, we may cancel these common factors. That gives us the required result and also concludes the discussion of problem 3. Okay, let's have a look at the first part of problem 4. We will again use the implicit function theorem. For that, our first step is to find the partial derivatives of f. You can check the calculations of these partial derivatives. We note that the first order partial derivatives of f are continuous. For alpha equals 5, the point with coordinates alpha plus 1, negative alpha minus 1, alpha plus 1 is the point with coordinates 6, negative 6, 6. Obviously, if you have a different value for alpha, you will find a different point. We continue to check the conditions of the implicit function theorem, and we notice that the function value of f at the point 6, negative 6, 6 is indeed 0, but the function value of the partial derivative of f with respect to z at the same point is not 0. We have shown that the conditions of the implicit function theorem are met, and so we can conclude that the equation f at x, y, z equals 0 determines z as a differentiable function, lowercase f, of x and y. Since the function lowercase f is differentiable at the point 6, negative 6, by definition 73, the tangent plane to the graph of f exists at the point 6, negative 6, 6 on the surface. Now let's have a look at the second part of problem 4. We will obviously use the result that we obtained in the first part. Remember that the first part gave us a differentiable function lowercase f of x and y according to the implicit function theorem. For that function we now have the following. In the first instance, the function value of f at 6, negative 6 must be equal to 6. Also, we can use the implicit function theorem to find the partial derivatives of lowercase f with respect to x and y. For the partial derivative with respect to x at the point 6, negative 6, we get the value 4. For the partial derivative of lowercase f with respect to y, we get the value at the point 6, negative 6 is equal to 3. You are welcome to check these calculations. Finally, we can use the standard form for the equation of the tangent plane. That is, z is the function value at the point plus the partial derivative with respect to f at the point times x minus 6. That 6 is the x coordinate of the point plus the partial derivative with respect to y at the given point times y minus the y value of the point, which is negative 6 in this case. And we then just simplify. We know what the values of the partial derivatives are, and we know what the value of the function is at the point. That concludes the discussion of problem 4 and also the discussion of assignment 7.